Swayam Prabha. Digital India. Educated India.
Now we are going to go to the fourth module related to PCA, PCA using data matrix, empirical orthogonal function. That is the topic. So let us look at this PCA. There are two types of analysis. One is the population based PCA. Here I am assuming X is a vector, mu and sigma, the mean and the covariance are known, and sigma is SPD. We then do an eigen decomposition, then we project X onto the eigenspace. So we get a new representation of X in the orthogonal basis formed by the eigenvectors. From here I am going to reconstruct the signal, reconstruct X which is X bar. I am using K components. The K is chosen for a given beta, beta is very small, 1 minus beta is very large. The K components together is going to give you a total variance which is at least as large as 1 minus beta, where beta is small, beta is 0.1, 0.01, 0.05 and so on. So this is the theoretical analysis, this is the theoretical basis for doing the PCA. But in practice we don't know mu, we don't know the matrix sigma. We are only given a bunch of data which I have organized in the form of a matrix. So this analysis is a sample based counterpart of the population based. Why it's called population based? I know the population distribution, if not the entire distribution, I know the first two moments, mu and sigma, the mean and the covariance. Here mu and sigma are not known, we simply have to work with data. We need to generate everything that we need simply based on data. So we need to estimate mu, mu hat, sigma hat which is the estimate of sigma. PCA analysis, I am going to repeat the whole PCA analysis not on mu and sigma because they are not known, but on mu hat and sigma hat. So this part of PCA applied to the estimates of mean and the covariance is called sample based PCA. More often than not, when people say PCA, they refer to this part of the analysis. Another technical term for this is empirical orthogonal function based analysis. Let us talk about this. What is this empirical? Sigma hat is an empirical estimate of the covariance. Orthogonal eigenvectors of sigma in the original analysis. Now I am going to replace sigma with sigma hat. Assuming sigma hat is a positive definite matrix, I can do an eigen decomposition of sigma hat. Once I do the eigen decomposition of sigma hat, I am going to get the eigenvalues and eigenvectors. The eigenvectors of any symmetric positive definite matrix must be orthogonal. So the orthogonal eigenbases, which are the eigenvectors of the estimated matrix sigma hat, our analysis is going to be based on that, and that is why it is called empirical. Empirical because of estimate, orthogonal because eigenvectors of a real symmetric positive definite matrix are orthogonal. So this is the technical term. So PCA, empirical analysis, one representing population based, another representing data based. We assume that raw data matrix is X. Please understand, now I am replacing a random vector X of dimension m by a random data matrix of dimension m cross n. What does it mean? I have n columns, each of which are realizations of the vector x. So that's an ensemble of data I have collected. So the first step in EOF analysis is to extract the underlying covariance correlation structure of the data. So I need to fill up what I don't have. So this calls for transformation of data. First, I need to be able to center the variables. Then I need to be able to normalize the variables if the units across the various rows are different. For example, if I have attribute, first attribute is weight, second attribute is height. If I express weight in kilograms, the numbers are going to be small. If I express weight in pounds, the numbers are going to be large. If I express the weight in ounces, it is going to be very large because the unit is very small. Likewise, the height I can represent in terms of centimeters, meters, millimeter, feet, inches. So depending on the units of measurements, the value of the particular measured quantity attribute may be large or small. When you are doing computations with various different attributes, if the units of one attribute and the units of other attribute differ vastly, namely some entries are too large, some entries are too small, we want to make sure the small entries are not overly dominated by large entries. So we need to be able to normalize. So what is that we need to do? We need to bring in democracy. We need to make sure all the data items have similar say, if not the same say, in the decision process. Not doing this normalization will give more importance to larger values than smaller values. So we don't like that in the data analysis because we want every data item, if you have measured, it should have some implication on the decision process. So centering is simply subtracting the mean, normalizing is simply trying to divide by a scale factor. The scale factor depends on the units. So centering and scaling are two of the fundamental operations that one may have to perform on a given data matrix before you start the analysis. You don't start the analysis blindly on the given data matrix. Now let's say centering. If you consider the column, each elements of the column may have different units. So if I am going to compute the averages, I can't compute the averages of apples and oranges. I have to compute the averages of apples, averages of oranges. So the units of quantities across a column are different, but unit of quantities across the same row are the same. There could be weight, there could be color of the eyes, there could be salary level. So row averages of the data matrix is meaningful, column averages does not have any meaning. So in order to be able to perform these averages, I am going to express certain matrix, I am going to introduce certain matrix operation using which I can compute the quantities needed for centering, the quantities needed for scaling. So let Jn be a vector of size all ones, size of n. So let Jn be a column vector, all of whose elements are 1. For example, J4 is this. Let m be a vector of size m, where m1 is the row, the first row of elements, m2 is the second row of elements, mm is the last row of elements. So mi is 1 over n, j running from 1 to n of xij. So how can I express this sum in terms of matrix operation? J is a column vector of all ones. So this summation is equivalent to multiplying the ith row, the inner product of the ith row with the column vector Jn. So xi star Jn is the inner product divided by 1 over n. Let m be a matrix that consists of all components m1, m2, mn. If I am going to have Mi depends on ith row, m depends on m1, m2, mn. So that's going to depend on first row, second row, third row, fourth row. So the equation 1 becomes equation 2 when I go from the ith column to I'm sorry, the ith element of the column vector m to the column vector m itself. So m is equal to 1 over n x, which is the data matrix, times jn. So I'm trying to compute the inner product of each row with jn and divided by n. So that gives you m is the vector of row averages. Now what is centering? The centered data is called x tilde. So x is the original data, mi is the row average vector, x tilde is xij tilde. So the centered data xij tilde is equal to xij minus mi. Please understand, every element in the same row are going to have to be subtracted by the same average. So mi is the same average for elements across the ith row. So xij tilde is equal to xij minus mi. This I running from 1 to m, j runs from 1 to n. So I can now describe x tilde, which is the centered data, which is x minus m times jn transpose. Now I want you to understand that m times jn transpose. M is a column vector, jn transpose is a row vector. So this is the matrix, each of whose columns are m, so on. This matrix is subtracted from this matrix, and that's equivalent to centering. So m jn transpose is the n by m outer product matrix. You remember the outer product matrix we talked about when we talked about vector spaces, and that's exactly what is applied in here. Now I would like to be able to normalize. To be able to normalize, I can normalize it by many constants. I can normalize it by the maximum value. I can normalize it by several different methods. So if z is a random variable that lies in the interval a to b, I'm sorry, let me call it y. If y is a normal random variable lying in the interval a to b, I can describe z is equal to y minus a divided by b minus a. So when y is equal to a, it will be 0. When y is equal to b, it will be 1. So in this case, z belongs to 0, 1. That's one form of normalization. Another form of normalization could be, this is z1, let us say z2. z2 could be equal to y divided by maximum, which is b minus a, the maximum value of the interval that b minus a. Another could be if y is a random variable, with the mean mu and variance sigma square, I can convert this z into y minus mu divided by sigma. So y is a random variable, mu is the mean and sigma is the standard deviation. So z will have a mean 0 and the standard deviation 1. So this is one form of normalization. There is other forms of normalization I already talked about. In here, I am going to use the normalization based on scaling by the standard deviation. To get the standard deviation, I need to know the variance. I don't know the variance, I have to estimate. So nothing is known, but I know the average. So let Si square be the sample variance of the ith row of x. The ith row has n elements. Mi is the average of the ith row. Xij is the jth element of the ith row. Xij minus mi square, this is the sum of the square of the j items. We have already seen two ways of estimating the variance. One is the biased and the another unbiased. When the true mean is known, I can divide by 1 over n. When the true mean is not known, I have to divide by n minus 1 because mi's depend on xi's. So there is a dependency. So I am trying to reduce the number of degrees of freedom from n to n minus 1. because mi depends on the n quantities I already talked about. So I am dividing by n minus 1 to get the sample estimate. This we have defined it to be the difference between the actual value and the mean. There's a centered data x tilde xij. So it is simply sum of the squares of the centered data divided by 1 over m. So if I can do this for each row has one variance. I am now going to normalize the data matrix. The normalized data matrix is going to be called x hat. So x tilde x hat. Original data, centered data, normalized data. And how the normalization comes in? Xij is essentially equal to Xij tilde divided by Si. This is very similar to what we have done. We said Z is equal to Y minus mu divided by sigma. I subtract the mean and divide by the standard deviation. The mu is not known, sigma is not known. I am trying to represent the mu and sigma by that sample counterpart, sample estimate. Now I am going to define a diagonal matrix because I have already calculated the variances of m rows. I am going to consider the diagonal matrix consisting of m sample variances. Now this diagonal matrix, the diagonal elements of them are positive because they are variances. If the data has variation, the variance must be positive. So what is one nice way of expressing x tilde, the relation between x tilde and x hat? The relation between x tilde and x hat, that means to get the x tilde, xij tilde is equal to xij hat is xij tilde divided by si. This operation is element wise. This element wise operation can be captured as a matrix operation. So x tilde is equal to d to the power minus half. Please understand, d to the power half is the square root of the diagonal matrix. When we talked about matrix theory and their application to modeling, we have talked about square root of a given matrix. If the diagonal elements of the matrix are positive, the square root consists of the positive square root. So d to the power of minus half, it is a reciprocal, it is the inverse of the square root of the diagonal matrix. So that matrix can be given by this. This is the ultimate form of data. So I converted x to x tilde to x hat. It is this x hat I am going to put into my algorithm. The further analysis depends on x hat, not on x tilde. Here x d to the power of minus half is given by the diagonal matrix consisting of all the standard deviation, computer standard deviation. Now I am going to consider the covariance of the matrix X. Please understand, the PCA analysis depends on sigma. I don't know it, so I have to consider the sample counterpart of it. So this is the sample covariance of the data. I need to calculate all the quantities that my theory needs. So the starting point of the PCA analysis is the covariance of the data matrix. To compute the covariance of the data matrix, I need to compute the row averages, I need to compute the row variances. From there, I am going to normalize, center and normalize to get x hat. So the covariance is using x tilde. So I have two versions now. Please understand, I have x tilde, x hat. So from here, I have generated these two matrices. The covariance matrix can be is a matrix Cij. It is defined by the inner product of Ik with Jk. I hope you understand. The Cij. So I am considering the ith element. I am considering for I not equal to j that one, for I is equal to j this is equal to s square. Therefore, the covariance matrix C is simply 1 over n minus 1 times x tilde times X tilde transpose. So from X tilde, I am computing the covariance matrix. Once I have the covariance matrix, I can also consider its close relative correlation matrix. Correlation matrix is obtained by the correlation of X, I should say correlation of X is given by X hat. So X tilde is used for covariance, X hat is used for correlation, and that comes from the definition of correlation and covariance. So by the same relation, I am going to use Rij, and I have the correlation. The correlation is given by X tilde transpose. So by using the definition of the relation between X hat and X tilde, I get this relation, and I do know this is the covariance matrix. So the covariance matrix is normalized by multiplying it by on the left and the right by square root of the inverse of the square root of the diagonal matrix. This you should know from basic definition of the correlation, and it's also easy to prove that the elements of the correlation matrix are all less than equal, absolute value of the correlation is less than or equal to 1. Please understand, correlation is a normalized covariance. It is supposed to lie in the interval -1 to +1, -1, 0, +1. If it lies in this region, positively correlated. If it lies in this region, negatively correlated. If the correlation is 0, they are uncorrelated. If the correlation is +1, is it totally positively correlated. If the correlation is -1, is totally negatively correlated. Two positively correlated quantities, they increase together. Two negatively correlated quantities, you expect them to decrease together. So it is this ability to predict, knowing one and the correlation about the other quantity is fundamental to prediction in empirical processes. So what is the prelude to SVD analysis? Now, why are we doing this? PCA on the data. So let's bring in the notion of singular value decomposition. So there are lots of little things happening in here. We talked about the theory of PCA. Now we talked about various sources of data. I process the data to be able to compute the covariance. So to be able to do the covariance, the PCA, I need to concentrate on the covariance matrix. So I can now do, once I have the covariance matrix, I can apply the theory of PCA as I have developed and get a PCA representation for this. So that's a straightforward application. Secondly, there is also another important aspect to applying PCA. You remember the matrix is m by n. Oftentimes in application, n is the number of objects you have to study. You can't change that. M is the dimension of the space in which I am going to represent objects. If m is very large, and if the eigenvalues of the covariance structure decreases very fast, we have learned that I should be able to express the same data set not using all the m components, but using only the k largest principal component. K is less than m. So the resulting representation using only the k features corresponding to the k maximum eigenvalue, k less than m, that implies dimension reduction. So by doing a PCA analysis on a given data matrix, I can get an equivalent representation of the data, an equivalent approximate representation of the data. The quality of the approximation depends on the beta and the associated value of k. So we may be able to exclude the noise component by separating the signal from the noise and be able to analyze the signal alone, and signal can be represented in dimension k as opposed to dimension m when k is less than m, and k will definitely be less than m if the eigenvalues of the covariance matrix decrease very fast. That is the idea. We have already talked about the theoretical basis for the singular value decomposition analysis when we discussed modeling as well as least square solutions. So, we are now going to combine PCA, the sample based analysis, SVD, dimensional reduction, all these come into a hue in this analysis part. Recall that if we multiply a matrix H by a constant alpha, the non-zero eigenvalues of H transpose H and H transpose also get multiplied by alpha square. The eigenvalues of H transpose H are called the singular values of H. If the eigenvalues of H transpose H is multiplied by alpha square, the singular values get multiplied by alpha. This is a fact that comes from matrix analysis. A quick review of the SVD analysis tells you the above theory can be applied to the SVD analysis of the data matrix. So, earlier we developed the SVD in terms of matrix H, which is m by n. Now, I have a data matrix X, X tilde, X hat. Each of these are also m by n matrices. So, except for the name change H to X tilde, H to X hat, H to X, matrix is a matrix. So, the entire theory of SVD as we have developed for H can be applied to the theory of analysis of either X or X tilde or X hat. That is a generic nature, that is the generic nature of the analysis. So, here I am dealing with X. Please understand I am using X only as a sake of illustration. X can be replaced by X tilde, X can be replaced by X hat. So, X is the raw data. So, if I define my H matrix as 1 over square root of 10 times X, the Gramian H transpose H, H transpose, this is n by n, this is m by m. You already know that relation. So, now I am going to do an SVD analysis based on covariance, that is X tilde. There is another name for X tilde, is called centered data. The centered data sometimes is also called anomaly. What is anomaly? If you look into almanacs, the almanacs will tell you what is the average temperature of December 23rd today. So, what is the average temperature, average computed over the past, let us say 100 years for this day? Today comes in, we observe the average temperature and calculate the average temperature at the end of the day. So, that is today's actual temperature observed, that is the long term average of today's temperature, the difference is called anomaly. So, sometime in meteorological circle they will say the following: today is going to be 2 degrees above average, today is going to be 2 degrees below average. In a class, your grade is 10 points above average, your grade is 3 points below average. So, I can either tell you your exact grade, or I can talk about the difference of your grade from the average. The difference of your grade from the average is called anomaly. Anomaly could be positive, anomaly could be negative. So, knowing the average and the anomaly is equivalent to knowing the actual data. X tilde is sometimes called anomaly data matrix, it is also called centered data matrix. The H transpose H is in fact the covariance matrix, one of the Gramian, this is the other Gramian. So, now you can see the notion of Gramian, the notion of centering, the notion of covariance. Now, if I replace X by X hat, I get the correlation matrix. So I can do the PCA analysis by either using the raw data, or by using the centered data. I can or by using the centered and normalized data. With me? So I can talk about 3 different forms of analysis where H depends on X, H depends on X tilde, H depends on X hat. So X tilde, X hat come from the analysis. H is the generic matrix that we used in SVD. By associating H with one of these 3 matrices, I can bring to bear all the results from the SVD analysis of the matrix H. That's the idea. So if you set H is equal to 1 over square root of an X tilde, I get the normalized data matrix. That's called correlation based analysis. So the Gramian is correlation. So SVD analysis based on m greater than n. Consider the smaller of the 2 Gramian H transpose H. Lambda I be the eigenvector value pair of H transpose H, which is given by H transpose H Vi is equal to lambda I Vi. The lambda i's are listed in the decreasing order. The smallest value is greater than 0. Define the eigenvector matrix, define the eigenvalue matrix. So we get the eigen decomposition of the smaller of the 2 Gramian in equation 17. Case 1 continued. Now I am going to represent Ui is equal to 1 over square root of lambda I HV. This is a linear transformation of the eigenvectors of the smaller of the 2 Gramian. You can verify from the SVD theory that we did in the module on matrix decomposition. Lambda I Ui are the eigenvector eigenvalue pair for the larger Gramian HH transpose. So U is the vector. U is a matrix of vectors of eigenvalues. Eigenvectors of H, eigenvectors of the larger Gramian HH transpose. So I had V, now I am having U. You may recall HH transpose U is equal to U lambda. So from the relation 18, look at this now. The 18 is the one that relates the U to U, this must be VI, sorry, VI, that relates UI to VI. Therefore, HVI is equal to UI lambda to the power half, or HV, this is the component wise, this is the matrix wise. So the SVD of H is essentially U lambda to the power half V transpose. This is simply an outer product matrix UI VI. This is the m by n matrix multiplied by a scale factor square root of lambda I, which are the singular values of H, is a summation. So it's the weighted sum of outer product matrix. It is the additive decomposition of H, and that is the essence of SVD. I have already done this. I would like to be able to quickly recall the definitions in here. Likewise, I have the SVD for the case m cross n when n is greater than m. The smaller of the 2 Gramian HH transpose. So what is the basic idea? Always start with the smaller of the 2 Gramian. In one case H transpose H is smaller, in another case HH transpose is smaller. The same methodology follows. So I get 23, the arrangement of eigenvalues in the decreasing order, the smaller of the 2 Gramian. U is the eigenvectors of the larger Gramian coming from the linear transformation. 24 expresses the eigen decomposition of the larger Gramian. Again 26 relates Vi to Ui, which is the reverse of the previous case. So that essentially gives you the Gramian H transpose H, which is the larger of the 2 Gramian. So the new relation, the SVD is given by 29. Everything is parallel. It may look like I am going a little fast, but I am talking about the same quantity for the dual case where m is less than n. Therefore, the SVD of H in this particular case is given by this, which is again the sum of the outer product. So, the weighted sum of the outer product, the lambda I to the power half, I am sorry that I am messing it, lambda I to the power half the outer product matrix. So, 30 is the counterpart. Now, what is that we now know? We have an SVD for both m greater than n, m less than n. We work SVD in terms of H. H is the generic representation. By setting H to be x, x tilde, x hat, I can bring to bear the theory of SVD into the PCA analysis. So, we are trying to build a bridge by developing different mathematical tools. So, use of SVD to approximate H. So, that is the whole point of the game. So, the first two modules essentially tells you the theory. The third module tells you how to generate the data. The fourth module essentially tells you, if you do not know the actual population information, how to create the surrogate of the population information by estimates, and then parallels the development of the population based theory to this database, data matrix based development, data based development. So, SVD of H in 22 and 30 can be used for in two distinct ways to approximate H. First, we can use SVD to decompose H into a signal and a noise component. Please understand, the signal and the noise component is what we have already talked about. The noise is because of the low values of the variance. Signals are corresponding to the high values of the variance, which is lambdas. So, the lambda, the larger lambda represents signal, smaller lambda represents the noise. So, by separating the larger one from the smaller ones, to help separation I am going to help you with the beta. So, by choosing beta to be 0.1, 0.05, 0.01, and how do you decide this beta? That is a $1 million question. So, that is often decided by the plot of lambda. If it becomes flat in the tail end, the flat region of lambda in the tail end generally represents noise. Why? The noise has a variance which does not change. The noise variance is constant. So, when the bottom part of the variance becomes flat, the flat portion corresponds to the noise, this portion corresponds to the signal. But if it decreases like this, there is no small quantity here, the signal is very dominant, there is very little noise if any. Here there is more, the left there is more noise, the left there is no more noise, here there is much less noise. Second, we can use SVD to reduce the dimension of m of the data matrix to D, where D is less than m. That means I am going to replace H by H1 bar, which is going to be D by n, that is an approximation to H when m is very large. So, look at this now. There are two advantages. One is separation of signal from noise. Second, subsequently the representation of signal in using a smaller dimensional representation than the high dimensional representation of the original signal. It is this twin advantage is the basis for doing sample based analysis. So, reconstruction of the signal when n is greater than m, just for definiteness, I assume case 2. Please understand, case 1 is m greater than n, case 2 is n is greater than m. So, when m is greater than m, we call it tall matrix. The other case, this is m. In this case, we talk about a broad matrix 1 to m, This is 1, 2, n. So in this case, m is less than n. This is called broad matrix. So tall versus broad matrices, I am considering for the sake of illustration the broad matrix. Beta can be 0.1, 0.05, 0.1, etc. Let k be the smallest integer such that the sum of the k largest eigenvalues, which is the total variance contained in the k principal components, is greater than or equal to 1 minus beta times the total variance. This is the total. The lambda i's are ordered in the decreasing order as in 15 and 23. So the signal component of H1, is given, the signal component H1 of H is given by this matrix Ui versus Vi, outer product matrix, weighted by lambda I to the power half. They are singular values. So the sum of the outer product matrices is H1. What is H2? H minus H1, that is the outer product matrices coming from the last. So this is the sum of the m minus k. So this is the sum of k terms. This is the sum of m minus k terms corresponding to the least singular values, the least m minus k singular values. So this is the most, this is the least. So they are associated naturally with some optimality property. Recall H is equal to u lambda to the power half V transpose. U is m by n, lambda to the power half is n by n, V is r by n by n, H is m by n. So from the definition of K in 31, define partitions of U and V. So I have a matrix U, I can partition it into U1 and V1. This has contained K columns, this contains m minus K columns. Again, partition this. This is n columns, this is n minus K columns. Lambda to the power half, you partition it. The first K by K, this is m by m minus K, this is by, n minus K, this is n minus K. K by K, n minus K by n minus K, this is lambda 1, lambda 2. So by applying this partition to 34, we are going to get a very natural decomposition, of H, which becomes U1, U2, lambda that U1, U2, which essentially now becomes U1 lambda 1 to the power half V1 transpose. This is U2 lambda to the power half V2, this is H1 plus H2. Please understand, this is the signal component, this is the noise component. So we are able to separate the signal from the noise, provided we have a beta, provided we have a lambda that behaves like this. The lambda behaves. So H, the K lies somewhere here. K is a place where lambda becomes constant. If lambda becomes constant, signal always has larger representation in terms of eigenvalues. So I measure the quality of approximation. So in approximating H by H1, so what is that we are going to do? We are going to throw out H2. We are going to replace H by H1. Please understand, H is simply a representation of either x or x hat or x tilde. So working in the using H, I can apply this theory to x tilde, which is the covariance analysis for the PCA. So approximating H by H1, we need to develop a measure to quantify the goodness of this approximation again. To this end, we assume that the data matrix is a full rank. Please understand, the data matrix H is equal to either x, x tilde or x hat. The centering and normalization does not change the rank. So if the data matrix X is equal to a m by n matrix, if the data matrix m by n matrix is a full rank matrix, so rank of H, the rank of X is equal to minimum of m and n, which is equal to m in this case, because m is less than n, is the full rank matrix, which is m is less than m. So it turns out that signal part of H1 defined by 32 and 35 enjoys the property of being the best K-rank approximation to H, in the sense that the noise component of H2 has inherent minimality under suitably defined matrix norm. Therefore, H1 is equal to H minus H2, two matrices. I want to be able to measure the size of the matrix. To measure the size of the matrix, I have to use matrix norms, and that's what we are going to now relate that to. There are two kinds of norms. One is called the for analysis in here. One is called the Euclidean norm. Another is called the energy norm of a vector. Just to be able to relate, this must be capital A, Euclidean norm of a vector represented by A2, which is essentially square root of the sum of the squares. It is a measure of the generalized energy. I have already told you, Euclidean norm, the square of the Euclidean norm represents the energy in the vector associated with it. This energy is 0, only A is 0. In general, if A is not 0, the energy is not 0, there is a positive energy. The second one is called the Frobenius norm. We have already talked about Frobenius norm. The Frobenius norm is simply square root of the sum of the squares of the element of the matrix. So the F you don't consider here, the F is for the norm, sorry. So we consider this the Frobenius norm. The Frobenius norm is essentially square root of the sum of the squares. It is also, so if that means is the measure of the energy associated with the matrix. If the matrix A is 0, the energy is 0. So I can measure the energy of a vector by the Euclidean norm, the energy of the matrix by the Frobenius norm. Now we have a outer product matrix. I am again going to make it complete. I am going to introduce and to introduce the earlier definitions. U is a m vector, V is the n vector. Then B is equal to U V transpose is Ui Vj. That means I have U this. So that's going to be a matrix. The ijth element of this, is Vi. I'm sorry. The ijth element of this. This is going to be Ui. This is going to be Vj. So the ijth element of this is going to be Ui Vj. This matrix consists of columns which are multiples of U. This matrix consists of rows which are multiples of V. So every column is a multiple of one column. Every row is a multiple of one column. Therefore, it is a rank 1 matrix. As an example, when m is 3, n is 2, this is U, this is V, this is the matrix, outer product matrix. This is just to remind you in case you want to recall what the outer product is all about. And why are we talking about outer product matrix? Because the H1 is simply weighted sum of the outer product matrices. So what is the energy of an outer product matrix? The Frobenius norm is equal to sum of Ui square Vj square. I and j are two separate indices. I can separate this, I can separate this. This is simply the norm of U, square of the norm of U times the square of the norm of V. If U and V are unit vectors, then the square of the norm of that is UV transpose the outer product square of the Frobenius norm of that. So that essentially comes from the definition of the Frobenius norm. Now I am going to relate Frobenius norm to another quantity that I can compute easily, a property of the Frobenius norm. If A is a m by n matrix, the Frobenius norm of A can be verified to be the trace of AA transpose. Again, I am going to illustrate by an example. If A is ABCD, AA transpose is this, the Frobenius norm of this is simply a square plus b square plus c square plus d square. This is a square plus b square, c plus d square. So this relation is verified. This relation is verified. I'm simply trying to talk about some of the properties of the Frobenius norm. So energy in the noise component of H2. So please understand, if I'm trying to throw away something, I want to compute the measure of the size of what is being thrown. One measure of the size of what is being thrown is the size of the matrix. Energy norm of what is being thrown is a quantity that tells you how much you are throwing things out. So from 35 and 36 in this, the Frobenius norm of H2 is trace of H2 transpose. H2 is equal to U2 lambda to the power half V2 transpose times this. V2 transpose is identity. Lambda to the power half is lambda 2. So this becomes U2 lambda 2 U2 to the power half. And so we also know trace of ABC is equal to trace of BCA. This is equal to trace of ABC. I'm sorry. I made a mistake. This is equal to trace of CAB. This is equal to trace of BCA. That's right. Circular shift. By applying this formula in here, you can really see this is equal to the outer product of that. So this is going to be summation lambda I UI transpose, UI transpose. UI transpose is 1. Therefore, this quantity now becomes equal to summation lambda I is equal to k plus 1 to m. I hope this derivation is clear to all of you. I'm simply using matrix multiplication, the properties of traces and its relation to various matrices. So what does this mean? The norm of the energy that is being thrown out is simply the summation of the smallest n minus k eigenvalues. In the earlier modules, we have already shown this is the optimal, this is the lowest possible. So the optimality of the signal component of H1, in the light of the ordering of the lambda i's, the square of the Frobenius norm of H2 is the sum of the least eigenvalues of the smaller of the two Gramian HH transpose. Therefore, the Frobenius norm of the quantity that is being thrown is the minimum for any k that satisfies 31. And what is 31? 31 relates to, let's look at that now. Let's go back to look at 31. 31 is the one that satisfies this inequality. I'm going to pick k out of the m, the k largest. So this what is being thrown out is the minimum. What is being thrown out is the sum of the last m minus k eigenvalues, which is the minimum. So that's a similar argument applies to m greater than n as in case 1. We encourage the reader to fill out the details. So look at this now. Sometimes I assume m greater than n and do the analysis. Sometimes I want to do the complementary for the sake of completeness. So in this analysis, I assumed n is greater than m, that means broad matrix. So the theory is applicable to broad matrices as well as tall matrices. I demonstrated the application of this to broad matrix. I would like you to fill out the details for applying for the tall matrix. So we have shown the optimality. Now I am coming to the dimensional reduction, which is one of the fundamental goals of PCA. So from 15, I have u lambda to the power half v transpose is the SVD representation of H. Please understand, H is a generic variable. H represents the data. H is either x or x tilde or x hat. In the PCA analysis, I generally use x tilde, the anomaly matrix. So u is m by n, lambda to the power of n by n, v is n by n, UU transpose, VV transpose. So 45 now becomes H bar is equal to, okay. So 45, U is the matrix of orthogonal columns. So I can multiply 45 on the left by U transpose. So H bar is equal to U transpose H. This is U transpose U lambda to the power half V transpose. So that essentially becomes lambda to the power half V transpose. Lambda to the power half is a diagonal matrix. V, matrix of columns. V transpose, the columns of V are the rows. When you multiply a matrix on the left by a diagonal matrix, the diagonal elements are multiplied by the multiplying the rows. If you multiply a matrix by a diagonal element, the columns are getting multiplied by the diagonal elements. So this is called the row scaling, scaling of the rows of that, scaling of the rows of that. So that's a very fundamental relation that comes from SVD, equation 48. Now a useful partition of U, V and lambda, we have already done that. Go back. Instead of calling it K, I am calling it D. D is used in place of K. What is K? K is the sum of the largest K eigenvalues whose sum is greater than or equal to 1 minus beta times the total sum of the eigenvalues. So U is U1, U2, V is V1, V2, lambda is lambda 1 to the power half, lambda 2 to the power half, U1 transpose U1, U2 transpose U2. These are all the matrices, properties of matrices that come from the partitioning. So we are going to partition the left hand side of 47. Substituting these partitions the left hand side of 47 and simplifying, H bar becomes this, H becomes this. So H bar is equal to H1 bar, H2 bar. Now H1 bar is essentially D by N. H2 bar is M minus D by N. So what is that? This is M. I'm cutting it in here. This is D. This is M minus D. So I'm going to throw away the M minus D part. The D part is remaining. The D part contains total variance, which is 1 minus beta times the total variance. So this is the noisy part. This is the signal part. Therefore, this ability to partition H bar like this as H1 bar and H2 bar. H1 bar contains the signal component and its dimension, the length of the vector in this submatrix is D. D is much less than M, and that's the reason we call it dimension reduction. Partitioning on the right hand side, again partitioning the right hand side is coming like this. So combining everything, the root partition, the basic partition, H bar is given by this partition, this partition, this partition, which is equal to lambda 1 to the power half V1 transpose, lambda 2 to the power half V2 transpose. So the original the data H bar is given by 47. H bar is simply transformed H. So there was H, we did the eigenstructure for the smaller Gramian, larger Gramian. U is the vectors of eigenvectors for the larger Gramian. U is the matrix with orthonormal columns. So I am trying to multiply this by U transpose. So what is H bar? H bar is simply orthogonally transformed data matrix. Orthogonally transformed data matrix. Orthogonally transformed data matrix. And that's what H bar is, orthogonally transformed H. And that can be split into two submatrices. That can be split into two submatrices in here. So approximation of H by H1, which is called a dimension reduction DR. So H1 bar is a D by N matrix called the D-dimensional approximation to H, which is M by N matrix. and D is less than m. It turns out this representation of H by H1 has a natural optimality property as proved below. We have already proved it, I just want to be able to reinforce that. The energy in H2 bar is m minus D by n. So, by definition, the Frobenius square of the Frobenius norm of H bar is the sum of the Frobenius norm of H1 bar and H2 bar. I want you to be able to verify this, the sum of the two. So, this is the part we are going to keep, this is the part we are going to drop. The energy of the part that is going to drop is given by this, that is equal to H2 bar, which when H2 bar has a natural representation. So, this is identity. So, this is equal to trace of lambda 2, which is the sum of the eigenvalues, least of the eigenvalues. You have heard this couple of times now. So, in the light of this ordering of 15, for what is the ordering of 15? From maximum to minimum of the eigenvalues which represent the variances. The right hand side of 52 is the sum of the least n minus d eigenvalues of the smaller of the two Gramian H transpose H. Hence, H1 bar enjoys the inherent optimality property. So, this is called optimally reduced dimensional representation of H. So, I can reduce the dimension by projecting to a subspace. If I project it to any subspace, I get an arbitrary projection, arbitrary reduction. Please understand, we are never satisfied with arbitrary projection or arbitrary reduction. We want optimal results, optimal reduction. So, this is the optimally reduced representation, optimality in the sense of keeping only the k largest components, throwing away m minus k smallest component. All this is possible only under one circumstance, which I am now going to conclude once more. There can be two types of observed eigenstructure, one like this, one like this. So, this is case 1, this is case 2. In case 1, we already have seen I can pick either k or d, k is equal to d. This is the maximum number of eigenvalues which are signal component, the m minus, this is k, this is m minus k. So, in here the variance, even the minimum variance is so large, I cannot afford to drop it, and the eigenvalues are decreasing, they do not attain a plateau. One of the important properties of the noise vector is that the noise has a constant variance. So, it looks like this representation, the representation 2, I can't reduce. So, in here no reduction possible, in here reduction is possible. It is this ability to bring about the reduction, optimal reduction in the representation instead of m to d. Another way of looking at it, so this is the idea when the reduction is possible. So, I want to remind you that dimensional reduction is not always possible, it depends on the eigenstructure of the covariance matrix and how fast, how fast the eigenvalues decrease. Another way of representing this, another way of looking at it is like this. There is a space Rm. If I have a matrix m by n, so this is the matrix X, which is the m by n matrix. This can be considered as n points in the m dimensional space, n points. I am sorry. This can be considered as n points in the m dimensional space. I am going to have to map again to the d dimensional space, and d is less than n. Again there are n points. Please understand, there is a saying, you cannot throw the baby out with the bath water. So, there is a tub, you give bath to the baby, after giving a shower to the baby, you throw just the water, but not the baby. So do not throw the baby out with the bath water. Don't throw the signal, only throw the noise. So what is PCA? PCA using SVD helps you to bring about dimensional reduction. Bring about dimensional reduction. So this is the central role of PCA in data analysis, and is used repeatedly in several application areas. And what is another observation? This PCA is data dependent analysis. Why is it data dependence? It depends on the matrix X, X tilde, X hat, and H being able to set to one of this X or X tilde or X hat. So every analysis depends on the SVD of H, which is either X or X tilde, X hat. And this is the different ways of representing the data. So this is the data dependent representation. It's an optimal representation. Optimal representation. And these are the two basic properties of PCA as a tool for dimensional reduction. With this, we conclude our coverage of PCA related material. Thank you.